They say find z.30. That's the question, right? That means z alpha is the value of z such that alpha is the area in the right tail. So, they're telling you that this is 0.30. Find this. That's the question. Follow me? So you're simply going to go to the t-table. Let's pull out our t-tables. So the t-table looks like this. And you go to 0.30, which doesn't exist on this table, right? There's no 0.30 on here. So let's look at the other t-table. There are two. Here's the other one. This one does happen to have a 0.30 column. So 0.30 all the way down to the last row. 0.524. So this value is 0.524. So if the question says that x is normal with mean 200, 16, find the cutoff. Find the cutoff for the top 30% of this distribution. If that's the question, then you would say 0.524. It's positive because it's to the right of 0, is equal to x minus 200, that's the mean, divided by sigma squared, divided by sigma. This is sigma squared. So sigma squared equals 16, sigma equals 4. So x minus mu over sigma. Cross multiply. 0.524 times 4 plus 200 equals x. That's how you would do this by hand. Does that answer your question? Okay. There's another way to do this, and that's on the calculator. Did I show you that last time? Inverse norm, which is obtained by going second varies, which brings you to distributions. So inverse norm, percentile, so this is the 70th percentile, because if 0.30 is in the right tail, this is 0.70, right? So 0.7 comma mu 200 comma sigma, and you're done. So what does this give us? Let's check our answers, right? Let me grab my calculator. So second varies, inverse norm, 0.7 comma 200 comma 4. 202.098. 202.098. And what did we get? 0.524 times 4 plus 200. 202.096. So I'm good with the difference. It's not a big deal. Get it? Any questions with this? Okay, so let's move forward today. You are at a position now where you can do the whole homework that's due, the next homework, okay? I want you to do it by hand. I want you to check with the calculator. I want you to provide both answers. Make sure you come really close. So you will be able to do all of those now. Okay, so let's start on page 9 of the typed notes. I'm here. Did we do page 7? I believe I did, right? With the weights that are normal.
Not the bottom part.
Not a large group of women in Chicago? No? You want to finish that up first? Okay. Would you like to try? Just use your calculator for now. Listen, you're going to learn how to do it by hand, but on the exam, you're going to use your calculator. You're going to have 75 questions. So once you realize what's going on and such, you're going to jump to the calculator. So jump to the calculator now. What is the probability that a randomly selected woman from this group weighs less than 140 pounds? So the question is, find the probability that X is less than 140. Right? Where X is given to be normal with mean 145 and sigma equals 12.5. Notice that I write sigma equals 12.5 this time, because if I just wrote plain old 12.5, that would mean sigma squared. That would be the variance, and that's not the case. So I have to specify. If they give me sigma, I have to say sigma equals. Okay, so what's the command? Let's go, guys. Talk to me. What is it? Yep, norm CDF. What? Left, right, mu, sigma. So let's go. What is that?
Wouldn't left be just a large number because it's dealing with less than 140 pounds?
It would be large negative, right? Minus infinity. Choose any negative large number, minus 1,000, let's say, all the way to 140. So this is the right endpoint, in other words. Mu is 145, and sigma is 12.5. And I'm done. Get it? Next one. What is the probability that a randomly selected woman weighs more than 160 pounds? Probability X greater than 160. So this time, norm CDF. What do you say? Left endpoint what? 160. Right endpoint positive infinity. So any big number, 1,000 would be okay. Mu, 145. Sigma, 12.5. Next one. This is kind of the speed you'll have to be working on at your exam anyway. Next one. What is the probability that a randomly selected woman is between 120 and 150 pounds? Probability X lies between 120 and 150. So this time, left is 120 and right is 150. So norm CDF, 120, comma 150, comma 145, comma 12.5. What weight would be the 95th percentile? Here we go, inverse norm. 0.95, comma, mu, comma, sigma. Everybody okay? Do you want me to do anything by hand? Just let me know. How about we do this one by hand, because I want to use that in part E. Okay? Let's do this one by hand. What is the probability that a randomly selected woman is between 120 and 150 pounds? So I'm going to transform these to Z. So probability 120 minus 145 over sigma, 12.5. I'm using this formula, Z equals X minus mu over sigma. You're with me, right? Less than. Z less than 150 minus 145 over 12.5. So on the left side, I get -2 less than z less than 0.4. So let's go to -2 and positive 0.4. And I want this area. So I will take phi of 0.4. That means go look up the table. Minus phi of -2. Okay, so phi of 0.4 is what? Let's go to the z table. So I'm here. Phi of 0.4 is 0.6554. And phi of -2 is 0.0228. -2. 0.0228. And then I subtract 0.6554 minus 0.0228. 0.6326 is my final answer for that one. Everybody okay with this? So will you be doing this by hand on your test? The answer is no. You're just going to do Norm CDF and go on your merry way, right? Any questions? Yeah.
So they asked you, like for D, if what we would call in the 15th percentile, would you just do the same thing, 1 minus 2?
By hand? Are you saying how should you do that by hand?
Sure.
So you would start with Z, 0.95, 0.05. You would go to the T table and pick up the 0.05 number. So that would be 1.645. I'm here at the bottom of the 0.05 column. So 1.645. This was obtained from the T table 0.05 column. And then I still have to find the x that goes with that. So 1.645 equals x, I'm looking for x, minus mu, 145, over sigma, 12.5. So then I clean this up. I get 1.645 times 12.5 plus 145. 165.5625. X equals 165.5625. Like that, if I was doing it by hand. But really, if you just did this, you would have your answer. Follow? Is there confusion? There is, right? No? You good? Any other question? So let's do part E. Part E, this skip is for a different class, 102, okay? So what is the probability that among 10 women selected at random from this population, exactly 2 will be between 120 and 150 pounds? That's the question. What is the probability that among 10 women, so I'm dealing with 10 trials, 10 people, each person is a trial, selected at random from this population, exactly 2, changing this word 1 to 2, will be between 120 and 150 pounds. So this probability X lies between 120 and 150 was already found in part C. And the answer was 0.6326. I already found that up here. So I need to use that. Now it's saying the probability of success is 0.6326. So let me label that lowercase p for probability of success, meaning if the person has weight in that interval, 120 to 150 pounds, that is regarded as a success. That's what that's saying. And therefore, Q is the probability of failure. And that's 1 minus 0.6326. Because P and Q always add up to 1, right? So I'm going to use the binomial theorem. Remember we used binomial once before this semester? We used it when we were talking about the biased coin, which came out heads 0.65, probability 0.65, and we were doing Bayes' theorem. There was one other binomial problem. This is also a binomial problem. And although we will be discussing binomial theorem much more carefully later on this semester, maybe in a week or two, by the time we get there, you will be more than comfortable if I keep on throwing little binomial things at you. So, N is the number of trials, and I say that there are 10 women, so there are 10 trials. The probability of success per trial is 0.6326, and Q is its complement. And the question is saying, find the probability that exactly 2 will have weights in this interval. So find the probability of 2 successes, exactly 2 successes where R is the number of successes. Meaning, what is the probability that 2 women have weights in this category? Follow me? Yeah. Oh, I'm so sorry. There. We don't need all this. Let's get rid of it. There we are. Thanks for letting me know. So probability R equals 2. So this has a formula, binomial theorem. N choose R, P to the R, Q to the N minus R. Right? We've mentioned this before. Choose 2, 0.6326 to the 2, 1 minus 0.6326 to the 8th power. Because we're saying 2 women do have weights in this category, so I took that probability and raised it to the 2nd power, and 8 women don't, because if exactly 2 do, then the rest don't. And then this one gives you all the number of arrangements such that 2 do and 2 don't, meaning yes, yes, and 8 no's, or yes, no, yes, and 7 no's. You follow what I mean? Meaning this like this, or like this, or like this. And there are so many different combinations like that. How many will there be? 10 choose 2, which is 10 factorial over 2 factorial, 8 factorial, which is 90 over 2, which is 45. So there are 45 different ways to arrange the 2 who do have weights in that interval. Are you with me? So there's a good way to do this on your calculator. This would be binomial PDF N P R. So N is 10, P is 0.6326, and R is 2. Binomial PDF. So let's go to second VAERS again. That will bring you to distributions. So second VAERS, Go all the way down. Keep scrolling down. Binomial PDF is 0. That one. And then n is 10, comma, 0.6326, comma, and 2. Answer, 0.00597, or 8 rather. If you have a newer version of the TI-83 or TI-84, you won't have to put in commas. They will ask you number of trials, you'll say 10. Then you go to the next row. Probability P, 0.6326. And R is 2. So it'll just be a vertical table rather than horizontally. In the older versions, we put them in horizontally. Are you with me? Okay, the next question. I'm making this up, okay? So the next question says, find the probability of at most 2 women have weights between 120 and 150 pounds. At most 2 women. That means what? At most 2 means what? Who are included in there? 0, 1, 2. So probability of no women having weights in that interval, or every time you write or, it's going to be a plus. Probability of 1 woman, or probability of 2 women. So I would have to do binomial PDF 10.63260 plus binomial PDF 10.63261 plus binomial PDF 10.6326, comma 2, which is a pain, right? So there is a command which will take the sum of all these 3 and give it to you in just one step. And that is given by binomial CDF. C for cumulative. That means they will go and add up all these. If you just provide the N, which is 10, the P, which is 0.6326, and the R, which is the last one, meaning the 2. So if you say binomial CDF NP2, it will take the probability of 2 and the probability of 1 and the probability of 0 and add it up and give it to you in one step. So you don't have to do this 3 times. Get it? So that would be 2. And that would be your answer. So let's do it. Second, VARS, binomial CDF this time for cumulative, and 10, comma, 0.6326, comma, 2. 0.00679. Any questions? Yeah.
What if they ask the probability at least 2 women?
At least 2? That's my next one that I'm going to do. So probability at least 2. So who would that include? At least 2 means what? Right, 2 all the way to 10. So I could do all these 9 of them, binomial PDFs, which is a waste of time, right? So any other ideas?
Do the same thing up there, but the R would be 8.
Do the same thing up there, what?
But the R would be 8.
R would be 8. If the R was 8, I would add from 0 to 8. Is that what you want? You're getting there though, yeah?
You do 1 minus that.
Yeah, this is a PMF. It's a discrete distribution, right? Just let me show you what I mean. Probability of 0, 1, 2, dot, 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 probability of 10. These guys all add up to 1 because this is a probability mass function. Total probability is 1. This is a discrete distribution, right? You can't have 1.6498 women. So it's either 0 women, 1 woman, 2 women, 3 women, blah, 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 right? It's discrete. That means that all of these probabilities, here I'll write a distribution, xi, p of xi. So this is 0, 1, 2, dot, 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 10. So all of these guys add up to 1. So if I want the probability from 2 to 10, which is these, who's missing? These 2 are missing. So how about saying 1, which is the total of everybody, minus the missing ones. 1 minus probability of 0 and probability of 1. So I'll write here 1 minus the probability of 0 and 1. That's the sum of all the rest. And that's equal to 1 minus binomial CDF, cumulative, N, which is 10, P, which is 0.6326, and R, which is 1. R is 1 because, see this guy? That's the maximum value. 1. That's why it's 1. Get it? So let's get an answer. Oops, put it where you can see it. 1 minus second Ver's binomial CDF of 10 comma 0.6326 comma 1 0.9992. Yeah. Probability of 10 cumulative, so binomial CDF of NP10 would be 1, yes. Meaning 10 or 9 or 8 or 7 or 6 all the way down to 0. That adds up to 1. So yeah, why don't I write that here? Is equal to binomial CDF of NP10. Get it? Yeah.
What if you subtracted like 2 binomial CDFs? Like, you did 1 from 10 and then subtracted it from 1 from 2?
I don't understand.
Like, for one of the binom CDFs, your last number would be 10.
Yeah.
And you subtract that from a binom CDF with a last number would be 2.
Then you get 3, 4, 5, 6, 7, 8, 9, 10. Probability.
So 2 wouldn't be included?
If you subtracted binomial CDF of 2, then you would be beginning at 3 because 0, 1, and 2 would be subtracted.
Okay, so if you subtracted 1.
I did. Binomial CDF of 1. And this one is binomial CDF of NP10.
Okay.
So I don't have to write.
I'm asking the same thing, like what you just did.
Yeah. So you would do binomial CDF of NP10, which is just 1, minus binomial CDF of NP1. Because if you said NP2, the probability of 2 would be taken away, and you don't want to take it away. You want to include it in your answer. Because your answer has to include all 9 of these. Everybody okay? So that's just a little bit of binomial. It's a discrete distribution. Binomial is an example of a discrete distribution. Any questions? Okay. So that brings me to page 9. So let's say that you have a large population and the mean of that population is unknown. Here. I have a population of size n, and I want mu, but it's unknown. Population mean is unknown. So I would like to take a random sample from this population of size n, lowercase n. Take a random sample of size lowercase n, and whatever you get for x bar n will serve as an estimate for mu. We know what this is called. This is inferential statistics, right? The process by which you take a random sample and use the sample statistic to estimate the unknown population parameter. We know that. Okay, the question is, when you do this, do you expect any error? So if I took 3 of you guys and said, okay, you guys are my sample, whatever I get for the sample mean, that's going to be my estimate for the mu for all 220 of us in this class, right? Do I expect any error? Certainly, lots of error, right? How big of an error do I expect? So that's my goal today, to talk about how much is the error if you take a sample of size n and you use x bar to estimate mu, what is my error? That's where I'm going today, okay? So let me take, and I'm here on page 9, I would like to start building a distribution of all the x bars that are possible. Meaning this is just one sample, right? But it's not just one sample that's possible from a population of size capital N. I can have lots and lots and lots of samples, as we know, right? N choose n, different samples. Capital N choose lowercase n, different samples are possible. So I would like to start building a distribution of all possible x bars so that if I take the standard deviation of that distribution of x bars, it will tell me how much on average an x bar varies from the mean. Because standard deviation tells me on the average how much does your scores vary from the mean. So let me do that. Let's start with, and I do that process here, you can follow along on page 9. Let's say that I have a large population of size n. N is the population size. And I choose to take samples of size 100. N is equal to 100. So I'm taking samples of size 100. Let's say that I'm interested in the length of the trout in the Delaware River. How long are the trout? How big are the trout in the Delaware? That's my interest. That's an infinite population for all intents and purposes, right? So let me start taking samples of 100 trout. So here's my first sample. Sample number 1, I have 100 values. I'm going to measure the x bar for that sample, meaning I have 100 trout. Let's add them all up, the lengths of them all up, and divide by 100, and then return them to the Delaware. So I have the first x bar for sample number 1, which is the sum of the 100 divided by 100. Are you with me? I threw that sample back in the Delaware, and then I'll do it again. Take another sample, sample number 2, another 100 values, another 100 trout, measure all their lengths, add them up, here, x1 plus ... x100 divided by 100. That's my x bar. Make note of that x bar and return those 100 trout to the Delaware. And keep doing this infinite number of times. But I have a life and I want to do some math instead of looking at trout, right? So I stop at 500. I do this 500 times. Because I'm assuming that 500 is a large enough number to give me a distribution. I'm saying whether I have 500 values or whether I have 50,000 values, it's not going to make a difference because 500 is large enough for me to create a shape of the distribution to see what I want. Agree? So now I have 500 different X bars here, 500 of them. Take them and create a histogram. We know how to create a histogram with 500 values, right? You will find that something very beautiful happens. E of X bar, which is the mean of this histogram. Why am I calling it E of X bar? I'm calling it E of X bar because the capital letter E stands for expected value, which is another way of saying mean. So this is the mean of all the X bars. So E of X bar is exactly the same as E of X. What is X? X is the population of all the trout in the Delaware. So I'm claiming that when I take the mean of this histogram of the means, don't forget, X bars are the means. So when I take the mean of this histogram, I end up with exactly the same value as the average of all the infinite trout in the Delaware. And sigma of X bar, so I'm taking the standard deviation of that histogram, is equal to sigma x divided by radical n. That's what I find. So what is this saying to me in words? This is saying the larger the sample that you take, and my sample here was sample of size 100, mind you, because I had 100 of them that I was adding together and dividing by 100 to find the mean. So this is saying the larger your sample, the smaller your error, because this is the standard error. This is called standard error of the mean, or SEM. Standard error of the mean. So it's saying the larger the sample you take, the less far away you are from the mean, because sigma is a measure of how close the values are to the mean. We know that, right? That's the definition of standard deviation. Standard deviation means, on the average, how far are you from the mean? So this is saying, if you take large samples, because you know that if your denominator gets larger and larger and larger, I know it's under the square root, but that doesn't matter. If n gets infinite, the square root gets infinite too, right? So the larger the sample, the smaller the error, because it's sitting in the denominator, and when you divide by a larger number, you get a smaller quotient. So the moral of this story is, if you want to come close to the mean, now the beauty is that the means are the same, right? The mean of the original population is the same as the mean of your histogram here. So the average amount by which things differ from the mean of the histogram is the same as the average amount that things differ from the mean of everybody, because the means are the same. So the moral of this story is, if you want to get close to the mean, take large samples. But you already know that intuitively, because if I said to you, if I said to our old class on Monday, I have 220 of you, and I want to find your mean weight, would I be better off taking a sample of size 5 from the 220 people, or a sample of size 55? Answer 55, because the larger the sample, the smaller the error. You already kind of know that, right? And this is saying that. This is saying take larger and larger samples if you want to come closer and closer to the mean. Follow me. Okay, now this is in case of a infinite population. All this is probably on the next page. Let me just go to the next page. Yeah. So here, it's saying that E of X bar is the same as the mu of the original population. And sigma x bar is equal to sigma x over rad n. Those are the two formulas that I had on the previous page. And of course, variance would be the square of the standard deviation. So this is saying sigma squared x bar is equal to sigma squared x over n, because I squared this quantity and I got that. Follow me? I'm saying variance is the square of the standard deviation, that's all. So I squared this guy to get this. So this is just me carrying on, making some notes. Let's go to the next page. Page 11. So we understand that as n increases, sigma x bar, which is equal to sigma x over rad n, decreases. We understand that. So it says the sample size is increased from 50 to 200. What is the effect on the standard error? So I'm saying that the sample size, which is lowercase n, old, was 50. It used to be 50. N new is 200. What is the effect on the standard error? So why don't I go like this? Sigma x bar, that's the standard error, new, over sigma x bar old equals sigma x over rad n new over sigma x over rad n old. So flip this fraction and you get, let me do it the right way, sigma x over rad n new times rad n old over sigma x. All I did was flip this denominator and bring it to the top. The sigmas cancel and I get radical n old over n new. So that would be radical 50 over 200, which is rad 1/4, which is 1/2. And then bring this guy back up. So right now it's saying this, sigma x bar new over sigma x bar old equals 1/2. So I want to bring him back up here. So I get sigma x bar new equals half of sigma x bar old. So it's saying that the new standard error will be half of the old standard error if you quadruple the sample size. It's no surprise because this change, look at this rad n here. This rad n has gone from rad 50 to rad 200. So in going from rad 50 to rad 200, haven't we multiplied by 4? And so I have a factor of 4 sitting in the denominator, and 1 over rad 4 is 1/2. So I'm saying that the new standard error will be 1/2 times the old standard error if you quadruple the sample size. So you can do this, or you can just eyeball it and say, this is a factor of 4 in going from here to 4, from 50 to 200, and because this 4 will sit in the denominator, I will now have 1 over rad 4 as my factor. So this is the factor right here. The factor with which you multiply is just rad n old over rad n new. And because 50 over 200 is 1/4, rad 1/4 is 1/2, finished. And by factor, I mean this number that you multiply by. So let's just clarify. Sigma x bar nu is equal to some factor, which is this, rad n old over rad n nu, times sigma x bar old. Put this on your cheat sheet, because now you can have a cheat sheet, a 3x5, right? So 3x5 is only about this big, folks, from here down, right? I gave an exam this morning and they had big cheat sheets like this and said, this is not 3x5? No, that is not 3x5. 3x5 is about this big, right? So you can have a 3x5 cheat sheet for your second exam, both sides with formulas. This will be the first formula that goes on there, right? Next one. I don't have time for next one. My time is up, right? So we'll continue on Monday.